for our final talk here of the day. I'm pleased to have our own Larry Wasserman, and Larry has done a large number of tremendous things over the years. I just want to point to that he recently earned a very prestigious award. I have to look at the name here. Forget. He was awarded from the Committee of Presidents of Statistical Societies, their highest honor, the Distinguished Achievement Award, recognizing meritorious achievement in scholarship in statistical sciences. We're very proud of that. Larry has won many such awards over the years, including one of another award from the same society, one of their other prestigious awards back in '99, which is awarded to achievement to a statistician under the age of 41. So apparently for this one, there was no age cap.
For this one, you have to be really old.
But again, we're so pleased to have him here. He's going to be talking about cows.
Okay, thanks, Jeff. You're going to embarrass me. So this will be a neural net free talk. No neural nets. There's no diffusion models. This is basic statistics. This is work with Chad and Mikhail. And actually, I should have added Alex's name because he joined the project. And I don't know if we'll get to that stuff. Is Alex in? Where is Alex? Right in front of me. So you'll see if I get to the later stuff, look at the stuff that Alex has been participating in too. Although the talk, I have to admit, is kind of long and I probably won't get to most of it. And the background here is that. Did I not? Yeah. So here's it. So we're going to start by talking about this thing called S weights and its generalization called cows. It goes back to Barlow in '87. So it's actually been around for a long time, although there is a generalization called cows. And what happened was Michael Schmeling, one of the authors of the cows paper, gave a PhiStat talk about that. And they asked Chad actually to give a discussion. And so Chad gave a nice discussion of that. And then Chad and Mikhail and I got us very interested in it. And we thought, it'd be kind of interesting to try to understand this algorithm better from a statistical perspective. And we ended up doing that. And we have a paper about that on arXiv. But also we decided, this is pretty interesting. And we thought of some variations of this idea that we can, that are very useful in other settings as well. We refer to those as hybrids. Yes, we do try to milk this for all of and you can't resist this stuff. So anyway, so I'll describe the basic. I know the particle physicists probably already know this algorithm, but for everybody else, I'll start at the beginning and describe the algorithm. It's a very simple but useful algorithm. And then our take on it, and then our extensions or hybrids of this algorithm. And like I said, I don't think I'll get to all of them in a half hour, but we'll see. So the setting is this, or the original setting is this. You have two variables, what we call the primary variable, or I think they call it the discriminant, and then there's a secondary variable they call the control variable. I'll use primary and secondary. So the primary variable you can think of as the mass of a particle, and T might be the decay time or something like that. And for the first variable, this primary variable, we know a lot about it. We have some sort of model. In particular, we have a mixture model. So there's a signal and a background, like some of the models we've seen earlier. And so pi here is the signal strength. S of m is the signal density. And then there's a background, and that has a density B of m. And we're either going to assume that in some cases this signal density and background density are known, or perhaps we have simulators from them, or we have at least a model for those densities. So the idea here is m is different because we know a lot about it. That's the key thing. So at the very least, we assume M has a well-defined model involving perhaps some parameters theta and gamma. But we want to know something about T. We want to estimate T, and we don't have all this information about T. So we don't have a good model for T. We don't have the background. We don't have the signal and so on. So the question is, how do you leverage the information about M to extract information about T? And the S weights, this is just to put a picture of these things kind of look like, at least in my mind. The signal for M might be some sort of localized thing in the background, maybe some decreasing smooth density. And so the assumption in the original S weights paper is this, that these variables M and T are conditionally independent. That is, among the signal outcomes, M and T are independent. And among the background events, they're also independent. They're not marginally independent, but they're conditionally independent in these two groups. And so that means I can write the joint density of M and T here. That's why it's a product. So we have the G and the H as a product because they're conditionally independent. And again, I've got the parameters in here, but H1 and H2 we don't know anything about. So that's the idea. We know much less about H and T. So from a statistical perspective, we would call this a semi-parametric model because there are Euclidean parameters, pi, theta, and gamma. But then these two other, the densities for the T variable, they're functions and they're completely unknown. And so those are what we would call infinite dimensional nuisance parameters. And the main interest actually is to recover those, to recover H1, H2, especially H1, the signal density for the second variable. And by the way, I'm giving you my understanding of all this. And there are some particle physicists here. Feel free to correct me if I'm explaining this wrong. One question immediately comes up is this model even identified? Could we estimate these things with an infinite amount of data? If I just write the model, I've dropped the parameters here and just written it more generally as a product of G's and H's. And written this way, are all these things identified? And it is identified because we're assuming, again, G1 and G2 are either known or lie in a family. If that was not the case, if we tried to let G and G1 and G2 also be non-parametric, then this model is not identified. There are you can't separate pi, G1, G2, H1, H2, even if you know this joint density P. Although a surprising fact is if you had a third variable, so now I've put in PMTU and I've used the same kind of model, so I've got pi times the product, 1 minus pi times the product. Rather surprisingly, once you get 3 or more variables, it is identified non-parametric. You wouldn't even need models for any of these things. And this is the part I might get to later, and this is where Alex has been working with us. So strangely enough, for 3 or more variables, it's completely non-parametrically identified. But for 2, we definitely need information about G1 and G2. So I'll come back to this point later if we have time. And I think that's a pretty striking and surprising fact. Okay, so let's go back to the 2 variable case though, and what what this S-weights algorithm does is, how would a statistician think of this? It's a semi-parametric model. We'd probably try to do something to try to estimate, maybe we'd expand H1 and H2 in a basis and do stuff. But actually they do something that we probably wouldn't have thought of, which is to construct 2 functions, weight functions, that pick out G1 and G2. So the inner product of W1 first weight and G is 1 and 0 the other against G2, and vice versa. W2 is orthogonal to G1 but picks out G2. And there's many ways to construct such weight functions. There's actually infinitely many ways to do it. But when you pick that, it's easy to see. A quick calculation shows you that you recover H1 and H2 because H1 is just the inner product between the first weight, and this is just a point mass here at T, and this is just dividing through by pi. And so what happens is if I just replace these expected values with averages, And if I replace the indicators with kernels, we get weighted kernel estimator. So this is a really simple way to recover H1 and H2. All I do is I just do a kernel density estimator. This is just a kernel with bandwidth H over T, but I use these weights, these special weights that we constructed. And now you have consistent estimates of H1 and H2. So a really simple way to recover these two functions. Very nice. And under standard conditions, one can show it's consistent and all that stuff. How do you construct the weight functions? Here's one way to do it. You choose any two arbitrary linearly independent functions, phi1 and phi2. And now all you do is the two weights are going to be linear combinations of phi1 and phi2. And the weights are just the inverse of this matrix A, and A is just this matrix that takes the inner products of the G's with the functions phi. And so it's very easy to construct such weights, and the construction is exactly to make sure it satisfies those conditions. You can even show if you minimize the mean squared error of your estimator over all such weights, then one can show that the optimal choice for the phi functions is actually the G's themselves. So you don't have to use that, but if you want optimality, you take the G's to generate as the phi's to generate then the weights. And if the G's are estimated, you just of course put estimates in. Okay. This is not the main interest, but you might wonder, how do we estimate pi? There's actually about 4 or 5 ways in our draft now for estimating pi. There's many ways to estimate the weight pi. The simplest one is it's easy to check that if you just take the average of the weight, you get pi. You just take the expected value of that. That gives you the estimator. There's several other ways. You can do take the marginal for M. Remember, is a known model. You can do maximum likelihood. That's another estimator. One thing we realized recently is none of those estimators are efficient, that is, have the smallest asymptotic variance. And so you can actually write down an estimating equation. The details here are not so important. There's something called the efficient score. It's some function that you set equal to 0, and you get the optimal estimator. But so I don't know if it's worth it. I don't know if it really improves the efficiency that much. But in principle, there's an optimal estimator. It's not the ones people have been using. We'll see that if I get to the more extended model with more variables, this turns out to be surprisingly complicated to get the efficient estimator. All right. By the way, here's a note on what not to do, because I think all three of us had the same reaction when we first saw this, their paper, which is, well, wait a second. If we just concentrate on the first variable m, it's just a mixture model. I can fit the mixture, and I can now say for every observation, what's the probability it came from group 1, what's the probability it came from group 2. I don't want to use those weights. That doesn't work. So, these are the weights you would get from the marginal mixture model, but you can see that if you take the expected weighted thing, then you get a biased estimate. It just doesn't work. It's just not the right thing to do. So these weights would be more intuitive in some sense because they're always positive. The weights that they have are actually kind of weird weights because they're negative too. They're not just positive or negative. So they're kind of strange weights in a way, but they're the right things to do to get the consistent estimate. Here's an example. This, I have to admit, I just knocked this off quickly when I made these slides, so that the estimates aren't going to look great. But what I'm showing here is the truth. This is G1. This is the signal for M. And this is G2. This is the background for M. And then this is the signal for T, which looks very different, as you can see in the background. And now I'll show you the estimates I got from a quick run of the S-weights algorithm. Again, I didn't put a lot of effort into this because you can see this boundary bias that I would get rid of, and I didn't try at all to optimize the bandwidth, because you can see this came out rough. But overall, actually, it did pretty good. I mean, this actually captures the basic shape of these two functions. With a little bit more effort, it actually comes out nicer. In fact, I think I put in, here's an example. that Chad did, which is much better. And it's just showing you again that when you apply this algorithm, you actually are I think the truth, the blue, and the orange becomes your estimate, right?
Yeah.
And so it's doing a fairly good job of capturing these functions. All right. Well, so what is cows though? So that's back in the 80s. Now, Michael Schmeling and his colleagues quite reasonably said, well, that conditional independence assumption is very strong. We'd like to weaken that. And the way they chose to do it, and again, this is sort of, for me, if I was going to weaken the conditional independence assumption, and we'll talk about how we did it later using a copula, but they thought of something completely different, which is they wanted to maintain that product structure because then you can use the same kind of algorithm. And so what they did was they said, well, we had a signal density, which was a product of two things. Let's take a mixture of mixtures. So let's take the signal now to be a mixture of those kind of conditional independence things. And do the same thing for the background. So it's a mixture of mixtures. And again, to me, this always troubled me at first, that this seemed like a strange thing to do, but it does now. It's no longer the case that these variables are conditionally independent, so it's weakened the independence assumption. But it still has that nice form. You can still construct weights for it and do everything, do all these same things. So we want to estimate, say, the signal density, which is now a linear combination of these H's, but the same thing works. We still need a marginal model. You still need this extra information about one of the margins. So in their paper, they're saying that we have this marginal model, and there could be parameters in it. And this has still got this, the signal is a mixture of some G's, and the background is some mixture of G's. So we either have these G's or we can estimate these G's. But because we have them, we can do the same trick. We can do these weights, which now there's going to be n of them. There's going to be a whole bunch of these weight functions, and they're going to satisfy the same conditions, that the inner product of the weight with one of the G functions is this delta function, 1 or 0. And then by exactly the same argument, you can see that the signal density can be recovered from the weight function. There's an indicator function there, which would be replaced with a kernel. And so at the end of the day, we just do another weighted kernel estimator. And so the nice thing about this is, again, an extremely easy, fast algorithm. It doesn't require anything complicated. It's now relaxed the conditional independence assumption, so it's a much more general thing. Again, to get the weights, similar kind of thing. You can choose an arbitrary set of linearly independent functions. You form the matrix A. You solve some equations, and you'll get these weights. You just have to do some matrix multiplication. It's all very simple and quick. There's nothing to it. And again, you can write down what the optimal weights are, which involve the G functions themselves. Okay. And there's like the standard asymptotic statements and everything that I won't go through. Now the first question comes out. We get to the herd of cows, which is that this sort of bothered us a bit, which is how did they get from S weights to cows? Let's think about what they actually did. Where did this model actually come from? Imagine I gave you the best possible amount of information, which is I'm going to tell you the marginal density for M, completely tell you the density. I'm going to tell you the signal density for M and the background density, and I'm going to tell you the mixing coefficient. Doesn't get any more informative than that. So this is like an idealized situation. I'm giving you all these functions. How do I get this cows model out of this? Well, what they do is they split this up into a sum, and they split this up into a sum to get a more flexible model. So what's happened is we now take a set of functions, G for the signal, and so we're going to write S as some linear combination of some basis functions, if you want to think of it that way. And we do the same thing for the background. We're going to break it up into a sum. And we have to make sure, by the way, that these functions are linearly independent, or this algorithm won't work. But I'm getting to an open question here, which is, There's infinitely many ways to do this, right? If I just give you a signal in the background and say, break it up into a mixture and break this one up into a mixture, there's infinitely many different ways of doing that. I'm still not clear how they actually do it in their paper. They just seem to pick functions. But once you do it, that gives you a cows model. And now every way of breaking it up, every way you can think of breaking it up, gives you a different cows model. And so what I don't know how to do is how to construct, in some sense, an optimal one. You could imagine doing a kind of forward selection procedure where maybe you start with a bunch of basis functions and you start dropping some of them into the signal bin and some of them into the background bin and try to approximate the function as accurately as possible or something like that, some sort of variable selection kind of procedure. But it's just not clear what the set of all such models, the herd, is the set of all such models, that would recover the correct joint density. I don't know what that is, and it's not even clear whether two different models would lead to the same estimate of the signal density that we're interested in. So is that identified or not? Are the different cows models lead to different estimators? And that's an open question. So how do we construct it? And does it matter which model we use and so on? It seems to be open questions. Okay, so now I want to get to some of these extensions that we came up with here. How am I doing? Let me just check the time.
You've got 10 minutes.
5 minutes? Yeah, 5 minutes. Okay, so I'm obviously not going to get through all this. This is going to be the second half of the talk. But I'll just do one or two, and then if you're interested, we have, like I say, we have the first paper about this is already on the archive, and the one we're writing with Alex will get on the archive in a couple of weeks, pretty soon, hopefully, which will have a lot of this stuff. Okay, so here are some extensions we thought of cows. So the first thing is this relates to, these assumptions. Remember that the basic model, the S-weights model we started with, really required a lot of knowledge about G1 and G2. They have to either be known or lie in a known parametric family. Otherwise, as I said, the model's not identified. That means you can't estimate everything, even with an infinite amount of data. But what we realized was even if they're completely unknown, you can still do something. It's true that H1 is not identified, but if we look back at the paper by Hall and Zhao in 2003, where they proved that this was not identified, if you look carefully at the proof, you realize that there is actually a kind of explicit one-parameter family. So in other words, if I give you the joint density, and we can always estimate the joint density, and I ask, well, okay, I can't identify these pieces, but they can't be arbitrary either. That this H1, we can ask, what are all the possible functions in that class? And you can actually get a hold of that. And so what you can get are bounds on this without making any assumptions about the margins. And so we were able to obtain these bounds. This is what two different examples look like. In this example, this is the estimate of H1 of t without any assumptions at all about the g's. And you can see in this particular example, you get pretty tight bounds. So it actually, even though it's doesn't nail down the function completely, it does you still get a lot of information. Then here's another example just to show you it's not always that good. In this case, we get these very wide bounds. And so there's another open question there, which is what are the situations in which you get tight bounds and what are the situations in which you don't get tight bounds? So that's one hybrid. Now I get to what I think is the most interesting hybrid, and this is where Alex has been working with us, is cows in higher dimensions, what we call Michi, which means, what does it mean again? Mixtures of conditional independence. Yeah. This gets to this point about there being, I said it was identified if there's three or more. So let's assume there are three or more variables. So now I'm just calling them X. So suppose we have variables X1 to XD. Now D I'm going to assume is 3 or bigger. Then what this model looks like, we're going to still, and also we're going to allow for K groups instead of 2 groups. So this is this Michi model. The density looks like this. It's the sum. So there's like the groups. And then within each group, we're still assuming conditional independence. And this is a well-studied model, actually. There's a lot of algorithms for trying to estimate the Fs. So this is non-parametrically identified, which means I don't have to assume any parametric models here. And I can estimate all of the Fs and the Pi's, which is sort of, again, surprising. And the current algorithms, though, are pretty complicated. So there's a lot of stuff to estimate, right? There's the Pi's, and then there's this matrix. You might think of it as all these functions here. So it has been studied quite a bit. I've listed some of the authors. And the point, since I'm running out of time, I'll just get to a kind of main point, is there are non-parametric EM algorithms for doing this. But they're all those algorithms are very, very iterative. And there isn't a unique maximum. But COWS gives you a very simple way to estimate this. So I'm going to skip all that. If you are willing to put a model down for one margin and only one margin, you just do the same thing that we just did. You just construct the weights the way we talked about, and now you do these weighted kernel estimators, and you've got all of the functions now in that model, no iterations to do, which is, I think, pretty nice. And in fact, there's a version of this we call robust cow, which is you put a model down for every margin, you repeat the whole COWS procedure, and then you do a model selection procedure afterwards, and you get a consistent estimator if at least one of those models is correct. So you get multiple robustness, which is, I think, very, very nice. And again, without any iterations or anything like that. So I guess I've run out of time. I'm just going to jump to the conclusion. This is a nice picture, Alex. Okay, there's your picture, Alex, showing this actually works, by the way. Sorry about this. There's another interesting hybrid we have here involving localized signals, and it uses all-to-all transport. It's too bad I won't have time to talk about it. And then we have a thing involving what are called copulas, which are a different way of dealing with the lack of independence. So yeah, hopefully at least this is an advertisement if you're interested to read the paper anyway. All right, so let me just go to the conclusions. So we were really unfamiliar with all these tools that the particle physicists developed, the S-weights and the COWS, but they're very interesting, and they provide really a whole set of tools for separating signal from background. The key is that it allows you to leverage information about one variable and use it for another variable. But I think there's lots of potential extensions. We talked about a couple here, and I've mentioned a few that we didn't get to, but I think there's probably other possible extensions as well. It seems like a very, very rich area. And that's it. Thanks.